for amplification of small time-varying signals, or you can use them to construct digital logic functions such as NOR gates, OR gates, okay, NAND gates. You can construct the Boolean algebra with transistor logic. Now, if the requirements are as such that you require a certain gain that might not be, for example, the required voltage gain may exceed with which can be obtained from a single transistor circuit, well, you might need to cascade two stages of MOSFETs, okay? Or in other words, let's say the requirements are as such that the output resistance, for example, over here, which is RO2, is supposed to be very small, okay? So, for example, the first stage, if amplification is required, could be a common source configuration. Then this stage can provide you the gain, okay? A small signal gain can be provided by the common source configuration of MOSFETs. Then in the next stage, you can use, for example, a source follower, okay? So next stage, you can have a source follower. The source follower has a lower output resistance, okay, a lower output impedance. So depending on the requirements, you might want to construct your circuit using cascaded or multi-stage MOSFET devices, okay. So it all depends on the requirements. So this is another application of MOSFET. So you see in most applications, the single transistor amplifier will not be able to meet the combined specifications of a given amplifier. For example, the input resistance, output resistance, etc., or the amplification factor. So transistor amplifier circuits can be connected in series or cascaded, as shown in figure 51. This is figure 51. These are generalized two-stage amplifier. You can have multiple stages, okay? You note that over here the gain is not necessarily equal to the product of two gains, AB1 and AB2. I mean, you need to consider the loading of one stage on another stage. So it's not that simple. It might not necessarily be equal to AB1 or AB2, okay? So, but anyways, for to keep the thing simple, you the thing is, I mean, you can cascade one or two or more stages to, for example, and again to improve the gain, or if the requirements are as such that you need a higher input resistance or you need the lower output resistance. It all depends on the requirements, okay. So transistor amplifier circuits, they can be connected in cascaded as shown in 51, and this may be done in either to increase the overall small signal voltage gain or provide an overall voltage gain that is greater than unity and with a very low output resistance. So now again, this voltage gain, it may not be simply the product of the individual amplification factors. Loading effects in general, they need to be taken into account for more practical applications. So the circuit in figure 52 over here, this is 52, over here you can see that you have a common source stage. The first stage is common source with MOSFET of M1. Then the other MOSFET M2 is in source follower. So the common source amplifier in the first stage provides a small signal voltage gain, and the source follower has a lower output resistance or not. So this is source follower. This is a source follower circuit. So let's try to analyze this circuit. I mean, looking at this circuit, if both the transistors are biased in the saturation region, we can use this for linear amplification purposes of an input signal Vi, okay, with a very low output resistance. I mean, the low output resistance means it can be cascaded, or it can be used to derive the loads. It can be used to drive, for example, for audio purposes, a loudspeaker, etc. So it doesn't load the next stage. So it can have a higher input resistance. So for example, this is a common source stage. Okay, the input resistance is large. So these CC over here and CS is a bypass capacitor, CC is a coupling capacitor that couples the AC signal over here. Then again, this is a coupling capacitor which will pass the AC to the load. But for the purpose of DC analysis, which we have considered so far, you don't need to consider the capacitors. All the capacitors are open for the capacitors. There are no capacitors if you want to consider the DC analysis. Okay, so they are all open. So let's consider an example. This is 3.17 of your course text. This is the design example. It says design the biasing of the multi-stage MOSFET circuit to meet the specific requirements. And you again consider this circuit of figure 52 over here. So I've copied the circuit over here. This is again figure 52. So we have to carry out the design. The specifications are as such that the transistors parameters, conduction parameters Kn1, Kn2 are similar, okay, for M1 and M2 devices. Both are NMOS devices. You can see the direction of current is as such, it's out of the source. So this is NMOS device. Threshold voltages are the same. VTN is given 1.2 volts. You don't need to consider the channel modulation effect. So basically M1 and M2 both are ideal MOSFETs. Okay. Even the forward resistance of those MOSFETs can be considered to be negligible, or you can assume that in the saturation you have a flat or a plateau region for the drain current. It's independent of VDS. Okay. If you need to consider the modulation parameter, then VDS has a role to play in the saturation region. Okay, I've explained this before. So if you consider this channel modulation parameter, then it's something like this instead of this. So we are consider the flat region. So you design the circuit. The quiescent current or the desired current in the first IDQ1 is given as 0.2 milliamps. Okay, so IDQ1, that's the drain to source current for the first MOSFET M1 is to be set at 0.2 milliamps, and this current is supposed to be the saturation current, okay, because we are looking for an amplifier. So we are going to consider the saturation IV characteristics to evaluate VGS1 and the other parameters associated with the MOSFET. Similarly, for IDQ2, we have the other, for the second MOSFET IDQ2, we are given the current of 0.5 milliamps. So this is 0.5 milliamps. This is what the design requirements are. So you are given, so for example, this Q points that are associated with the currents and the voltages. So this voltage is VDQ2. This is VDQ2 or VDSQ2. That's more appropriate. And then you have this VDSQ1, VDSQ1. So these are also specified as 6 volts. Both are 6 volts. Okay. So in order for them to be both MOSFETs to be in saturation region, we expect that this VDS Q1 and Q2 are greater than VDS saturation point. I mean, the transition, this has to cross the transition point, or should be greater than the transition point from non-sat to sat. Similarly, the input resistance is given as 100K, and RSI over here, the source resistance is given to you as 4K. Okay, 4K. But for DC analysis, you see this capacitor is open, so you're only considering the input resistance from this point. I mean, this is your input resistance. So you're looking inside towards the gate of the first MOSFET M1. Okay, this is your RI. All right, so you don't need to worry about the source resistance. Now, okay, now the thing is, the design requirements are as such. We are given the transistor parameters, conduction parameters, threshold voltages. You don't need to consider the modulation parameters. You need to design the circuit. So you are given the Q points. You're given the currents on both the transistor drain to source currents, and you're given the drain to source voltages. So what does it mean? I mean, what is it there to be designed? I mean, what you need to determine for the given voltages and the currents are the resistances. You need to determine R1. You need to determine R2 for the given input resistance, let's say. Then for the given currents, you need to determine what is RD1, what is RS1, similarly what is RS2. So you need to determine those resistances which are biasing the transistor such that you are for the given current, what is the question is what is VGS1, for example, okay, and then using this and what is VGS2, then using the IV relationship for the current and voltages in the saturation region. You find what is VGS, that gives the IDQ1. Then from that current you find what is the resistance. Okay, so that's how you determine the biasing, the DC biasing. Okay, so for the design, you have the Q points, you have the current and the voltages, VDS and IDQs. So what are the resistances that ensure these voltages and current? So that's what we are after now. Okay, so to start with, now for the output transistor M2, let's consider this M2. And if I consider this output loop, okay, forget about this part of the load. This is open. Okay, we are not going to consider this part. This is open. This is open. This is open. So we are only left with only this circuit. Okay, just consider this circuit. So if you consider the output loop, let's try to write a KVL for this loop. So you see over here, you have this, the drain of M2 is tied up to positive 5 volts. So I can write this as plus V plus. Then I have minus, this is VDQ2, or let's write this as VDSQ2, Q2 minus, what else do we have? There's a drop over here as well, okay? So let's write this as IDQ2 times RS2. Okay, this resistor over here, you see, is RS2. So I have to bring this over here. Then minus V negative. Okay, you have to add these voltages up, and then this sum should be equal to 0. So all we know is, what is VDSQ2, but this is required. So, well, you can write this as VDSQ2. Let's bring this to the other side of the equation where this 0 is, okay, and rearrange the terms. So you end up writing, so okay, I know what is V positive, that's 5 volts. And then I have minus, this minus V is minus 5. Okay, so let's put it like this. And the only unknown is RS2. Okay, we know what is IDQ2 as well. So IDQ2 is given as 0.5 milliamps. So if we write this as 0.5, then of course we are looking for the resistance in kilo ohms. Okay, so 0.5 multiplied by your RS2. So we have this precisely this equation, and this voltage is 6 volts. So this gives you what is RS2. So I mean, you have this equation over here. It's the same equation. This is from the Kirchhoff voltage law for the output loop of M2, and this VDSQ2 is V positive minus V negative minus the drop at the RS2. So this gives you, solving this gives you RS2 as 8 kilos. Now we have RS2, and for amplification, we have to bias the transistor in the active or the saturation region. So let's assume the transistor are biased in the saturation region. Let's use the current. So you see over here, the dependence of the IDQ2 is not on VDS. Okay, you don't need to depend on VDS. It is being determined by VGS2, which is the only unknown. We have Kn2, and Kn2, the conduction parameter for the second MOSFET, is given as 200 microamps, which is 0.2 milli. Okay, IDQ2 is also 0.5 milliamps. If you consider everything is in milli, then VDN is given as 1.2 volts. So the only unknown is your VGS2, which you can find from this quadratic, and this gives you VGS2 as 2.78 volts. Now, as a quick check, if this M2 is in the saturation region, you realize that your VDS sat 2, I must say VDS sat, if you write this as VDS sat for the second MOSFET, well, that is the transition point, and that is given by VGS2, this voltage 2.78 volt, so VGS2 minus VTN2. So if you put the values, well, what is this? Let's find it out. This is 2.78 minus 1.2. Okay, so this comes out to be equal to 1.58. Okay, 1.58 volts. And what is your VDSQ2? That is 6 volts. Okay, so VDSQ2 over here is 6 volts, which is much greater than, not well, which is still greater than beyond VDS sat. So that means your M2 transistor is indeed in the saturation region. Okay, so this is what we desire. We desire M2 is in saturation, and we also desire that M1 is also in saturation. So this can be used to amplify the input signal. Okay, all right. So so we have VGS2 right over here. All right. We have determined the first resistor that the RS2 is 8 kilo ohms, and The other thing is, if you look at this circuit, well, it's getting quite messy. Let's start with the fresh one. So it's the same circuit, okay? Now we have VGS2 has 2.78 volts, okay? VDSQ is that requires 6 volts. So VS2 is minus 1 volts. How do you get this? You see, you can write this as, well, this point is your VS2, okay? And this point is your VD2, the drain voltage. So basically your VDSQ2, which is 6 volts, it can be written as the difference of these two potential differences. So you can write this as 5, which is your VD2, okay, then minus VS2. So you can see that VS2 is minus 1 volts, okay. VS2 is minus 1 volts. You know what is VDS, so basically this is VD minus VS. So you can find this potential. Basically, the other way around to check this is, you see your VS2 is nothing but the voltage drop across the resistor R2, plus there you have this minus 5 volts as well over here. So let's sum this up. So you have V negative plus whatever is the drop across your, this will be ID2 multiplied by RS2. Basically it's the same thing. So V negative is minus 5 volts, and then you remember that this ID2 was 0.5 milliamps, and this RS2 is RS2 was 8 kilo ohms, okay, so this was 8 kilo ohms. That's what we determined. So if you multiply these two quantities, you're again left with 4 volts, and the net result is, the net VS2 is again minus 1 volt. I mean, I've done this extra step, it was not required, it's quite evident. So anyways, this RS2 was 8K, so if you consider the drop over here, then you add this up, and then you get the source 2, the potential at the source of second MOSFET. Okay, so it's this potential plus the drop at R2 plus minus 5, so that gives you minus 1 volt. Anyways, okay, so VS2 is minus 1 volts, right? And VGS2 is 2.78 volts. So what does it mean? It means VG2 minus VS2 is your 2.78 volts. Therefore, this implies, well, this equation, if you rearrange this equation, you come up with like this. You get the gate voltage. You know what is VS2? That's minus 1. So you get VG2 as 1.78 volts. Okay, and where is VG2? Well, VG2 is over here. So this is the potential, VG2. Then now this potential is connected to the drain of the first transistor, VD1. So you see VG2 and VD1 are the same potential. So the potential difference across this resistor, remember that we are after these resistances. So we have determined RS2 at 8K. Now we need RD1, RS1, and then after we need this voltage divider R1 and R2. So let's find out what this RD1 is. So this VG2 and VD1 are the same. So the potential difference is, so it's like this: V positive. The potential difference between this point and this point is plus 5 minus VD1 divided by the current, that is IDQ1. Let's recall what this current is. So therefore we can use this to find what the drain resistance is. So this is IDQ1, and this gives you precisely the drain resistance, RD1. So this ID1 for the first MOSFET is 0.2 milliamps. Okay, so this 0.2 milliamps comes over here. If you substitute the values in this expression, this is your ID, the current, IDQ1. So if you substitute these values over here, you find this out, as 5 minus VD1 is 1.78, which is VD2 over 0.2 is, so you get RD1 as 1. You get RD1 as 16.1 kilos. Basically, these resistances will ensure that you have the Q point in the saturation region, so the linear amplification of the input signal is possible. Okay, so we are after these resistances. The first thing, I mean, even in order to design an amplifier, you need to keep the MOSFET in the required saturation or the activity. The biasing should be as such that um, the Q point should, or the transistor should be biased. The DC biasing should be in the saturation region. Okay, so for that you need these resistances. So we are evaluating these resistances. Okay, so in order to put up the circuit, you need to first find these resistances. Okay, and connect the circuit, and then you have the linear amplification. Okay, you can derive this with a certain AC signal, and in the output it will be maybe a larger value of this the same frequency, and the amplitude will be large. Okay, linear amplification. So okay, now you see we have VD1. So we know what is VDSQ. VDSQ1 is, it's again 6 volts. Okay, that is the requirement. So VDS1, VDSQ1, VDSQ2 is 6 volts. Okay, so VDSQ1 is 6 volts. So the source voltage of M1 can be found as such. Okay, basically this VDSQ1 is again the difference between VD1 minus VS1, and that is 6 volts. That is 6 volts. Now we know what is VD and VD1 is, and VD1 is your VG2. So VG2 is 1.78 volts. So if you plug these values, then it is 1.78 minus 6 is your VS1. That's VS1. So this is what this equation is telling you about, and that's minus 4.22. Then again from this potential, minus 4.22, and then take the potential difference of this point, divide by IDQ1, which is the same current as 0.2 milliamps. This gives you RS1 as 3.9 kilo ohms. Okay, so we have RD1, we have RS1, then we have RS2. Now all we are left with is R1 and R2. Okay, and since we know that M1 is also supposed to be in the saturation region, we can find what VGS1 is. So using the current voltage relationship, conduction parameter is given for MOSFET. M1 is 0.5 milliamps per volt squares. Threshold voltage for both MOSFET is 1.2. So you just plug those values, you know what is IDQ1 is, then find VGS1 as 1.83 volts. Okay. And once again, if you just for the sake of curiosity, if you want to check this, the difference of VGS1 1.83 and the difference of the threshold voltage of MOSFET 1, that is VDN1 is 1.2. Okay, but take the difference, I'm left with 0.63 volts, and that determines the transition point of the MOSFET M1. So this transition is, well, your actual VDSQ is 6 volts. Okay, so 6 volts, 6 volt, which is VDSQ, is much greater than 0.63 volts. So indeed your MOSFET M1 is also in saturation region. So both MOSFETs are operating in saturation regions. This is saturation, and this is also saturation. All right. So indeed we are trying to bias these transistors in the active or saturation region. For that we need those resistances. Okay. All right. So now we have this VGS1. So from the voltage divider, you look at this circuit. The difference of V plus minus V is 10 volts. So R2, if you apply the voltage divider here at this point, and this is R2 over R1 plus R2, and the difference is 10 volts. And since we are writing this for VGS1, which is the difference between VG minus VS1, VG1 minus VS1 is your VGS1, which is already evaluated as 1.83 volts. Okay, so let's set this equation equal to 1.83 volts. All right. Also, note that forget about this coupling capacitor. Forget about this. This is open. This is open. So circuit is open from these points, these nodes. Okay. So if you look inside of this cascaded MOSFET structure, your input resistance is given as well. You can write this the voltage divided R2 or R1 plus R2 in terms of the input resistance, which is given. I mean, this can be written as 1 over R1, R1, R2. So 1 over R1, So this constitutes your basically the R1 and R2 is coming in parallel, and this is forming the input resistance because next you have this gate and oxide, which is a very high input resistance. So the input resistance of MOSFET is high. You don't need to consider it any further. Uh, it's open circuit. So the input resistance is R1, R2 in parallel. So R1, R2 are in parallel. Okay. So this is 1 over R1 basically into Ri, and Ri is the input resistance which is given. The input resistance requirement was 100 kilos. So let's substitute this value. Instead of this writing this divided, I mean you can write this equation as such. VGS1 was 1.83 volts. Okay. Then you have 1 over R1, and this combination, this is 10. Okay, the input resistance was 100 kilos. So R1, R2, R1 plus R2, it can be written as 100. This Ri is 100 basically. Okay, and 1 over R1 is here, 1 over R1 is here, and then the difference, this voltage is coming over here, and then you have this current and the resistance values. RS1 we have already evaluated as 3.9 kilos. So this RS1 is 3.9 kilo ohms, and we know what IDQ is. IDQ is the current, that is 0.2 milliamps through the MOSFET M1. So this is the voltage drop across RS1, okay, for the source voltage. So this yields R1 as 383 kilo ohms from Ri, which is 100k, and when R1 is 383 and Ri is 100, so if you use this equation, this equation, you can find what the R2 is. Okay, so you have R1. Okay, then from Ri, the input resistance, you can find the R2, and that comes up to 135k. So the command is that both transistors are biased in saturation region as assumed, which is desired for the linear amplifiers. Okay, so that's how we carry out the DC analysis. Basically, you know that these are in saturation region, so you need the current voltage relationship for saturation region, find VGS1, and then apply the voltage dividers to find what the gate and source voltage separately are, and then whatever the specifications are for the given input resistance and for the given ID Q points, define the resistances, and you're done with the biasing. Okay, the idea was to bias the multi-stage MOSFET, cascaded MOSFET in saturation region, and to use this configuration for the linear amplifier. Okay, that's all.